All right, students, we are talking about orbit, how to get to orbit, what that is all about. All right, so let's say we've got the Earth right here, and we have a tower up there at the top of the Earth, and it's a giant tower. It is 100 times bigger than Mount Everest, okay? So this thing is truly massive. And you climb up to that top of the tower and you throw something. It just kind of, you don't throw it very hard. And at the moment that it leaves your hand, it's in free fall. So it's going to, follow a parabolic arc here. It's just under the influence of gravity. It's going to fall down. And this is such an extreme view. It's kind of interesting. We can see that it goes farther than if you were just a lot closer in on the Earth and you just threw it that same distance. It would only travel here where everything kind of looked flat. But if you're really high up there and you throw it, it's going to go so far that the curvature of the Earth starts to play a part here. So then you're like, all right, I'm going to throw this thing a little bit harder. Maybe you're going to launch it. We're still going to launch it horizontally initially here. So it's going to go horizontally, but as soon as it leaves your hand, obviously, it's starting to fall, and it's falling closer and closer to the Earth. But because you're so high up there initially, as it starts falling, the Earth is starting to fall too, or the Earth is starting to curve, okay? And that actually is playing a role here, where even though you're falling and getting closer to the Earth, okay, the Earth is also kind of, like I said, falling away, and as a result, it takes longer for the object that you threw to hit the ground. And then finally, you're not quite there yet, but maybe you get some sort of propellant, you get some sort of gun or some sort of high-powered device to really sling this rock or whatever it is that you're throwing horizontally, and you throw really, really hard, and it goes, and it's falling, and it actually starts to kind of make the turn with the Earth, and because the Earth is pulling on it, but it's got such a high velocity. If the Earth wasn't here, it would just be going straight out here, no problem. But the Earth's gravity is pulling it closer and closer and closer. And you kind of see it kind of starts to wrap around the Earth. And then finally, you're like, all right, I get this. I'm going to attach some rocket engines onto the end of this to give us this crazy initial push. Okay, now we're not right after we let go, as it were. It's in free fall. But so we're not. It's not like we're thrusting. Got the. We're pushing on it all the way. And even though I'm going to put some rocket engines here, the rocket engines are just going to give one. Maybe I'm going to, just hold on to it real quick and then shut the engines off as soon as we let it go. So it just gives it a massive kick here, as it were. And so it's got a really, really, really large velocity, and it starts to go around and starts to fall, but as it falls, well, I drew that just maybe a little bit too close. Let's try that again here, shall we? It's going around, and it's falling, but as it's falling, the Earth is also falling. So I'm getting closer and closer and closer to the Earth. But the Earth is also falling away, and this didn't turn out exactly the way it was, because it kind of looks like we came back across there. But anyway, the point is, if I draw on this perfectly, and we're not going to do that take again, that when you get back to this same point, the rock which you threw so hard goes all the way around the Earth and hits you in the back of the head, and it hits you in the back of the head, or maybe you dodge out of the way just at the right moment, and it is still traveling at whatever the initial velocity it had when it left your hand. So if you threw it at 100 miles per hour horizontally, and it goes all the way around the Earth and comes back, and you're seeing this thing coming up fast at you, you duck, it still goes, it's going 100 miles an hour right here. That's awesome, because if it's going 100 miles a year around the second time, then it's going to just do that same thing all the way around again. And at that time, then you duck again, and then it goes all the way around, And the Earth's gravity just keeps pulling. It's constantly falling, but the Earth is also curving, as they say. And then eventually you just get tired of ducking and you say, forget this, I'm just going to climb down this giant tower. And then that object will continue forever, unless another object acts on it. It is now in circular orbit. And that's what a circular orbit means. And what orbit itself means is that you've got some sort of closed path around something else, and you're never adding any additional force to it. I mean, there's no engines on this thing. I gave it a crazy push at the beginning, and then it just goes, and it's just going to keep going and keep going around and around and around. And what we're talking about here is a circular orbit. Now, you make it go a little bit faster than this particular velocity, and it enters something called an elliptical orbit, which gets really cool. But we're not. This is just high school physics. So you're interested in that, you go ahead and take some more classes in college, or just look online. They got all kinds of videos on it on YouTube. Anyway, so that's orbit. That's what it takes to get into orbit. You've got to have two things going on. One is you've got to get really, really high. You've got to get high above the Earth's crust here, or above the Earth's surface, rather. High enough such that drag from the air does not play a part. So you've got to go way, 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 way up here where the air is just pretty much non-existent, or very, very few parts per billion here. So there's not any air molecules that you're bumping into to slow you down. Then the other thing that you need to do is not only get really, really, really high, but you need to go really, 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 really fast sideways. Okay? Those are the two ingredients that you have to have. Let me make sure that I'm still here in focus and in the frame. All right, we're doing fine. So, interesting side note, that's what rockets do, okay? In fact, now a lot of people think that rockets, just go straight up, and then I don't know what they think. Maybe they think all of a sudden it turns sideways, and then goes like that. That's actually really, really inefficient. If you ever are fortunate enough to go see a rocket launch, what actually happens is it does go up, but then very quickly it starts to turn sideways, and it is just as important, if not even more important, that those engines are still on as it's oriented sideways as it is just to get it to go up. Those engines have to do both things. They've got to go take it up till it gets into the thinnest parts of the atmosphere, even the part where the atmosphere is non-existent, and then be able to go sideways. So it's got to kick it that way as well. So anyway, that's one of the reasons if you watch a rocket launch on television, which hopefully we'll be able to do that as a class here. You'll see on the camera, the rocket starts actually going sideways, and you look at it and you're like, why is the rocket going sideways? And the answer is because it's going sideways, because it's trying to go as fast as it can horizontally to be able to get that velocity such that it will enter into orbit, a closed loop, as they say. So the question is, how fast does it need to go to get into orbit, right? Well, we can just pick any part right there. We'll just pick the object at that moment right there, and we can do a little bit of analysis on our satellite here. So imagine that this is going around. Maybe it's taking pictures, or maybe it's taking pictures this way, of the stars and stuff like that. That's always pretty cool. We have a radius that we could talk about. We could talk about the mass of the object. And if you think about what are the forces that are acting on our satellite at this type, it's at this moment right here, it's just weight. That's it. Like I said, we're not constantly pushing it at any time. We gave it a big, huge push right here, and then it's just gliding here. Constant velocity. Okay, so there's only weight, and that's going down towards the center of the Earth. So maybe I could also draw the picture right here. That might make a little bit more sense with weight going down. So when we draw the free body diagram, we're going to draw weight, the weight force, and that's going down. So the question is, what velocity does this need to be going in order to make that closed loop? So let's go ahead and we'll write Newton's second law, so summation of forces in the y direction, and it's weight, which is going down. So I'll write weight equals mass times acceleration in the y direction. And we know that acceleration is in the negative direction. So you get negative there, so we'll just cancel both of those out. So we'll say the mass of the object times the acceleration due to gravity is equal to the mass, and this acceleration, since we're traveling in a circle, is centripetal acceleration. So that's going to be v squared over r. And what do you know? We have another interesting situation where the mass is on both sides, so we'll divide both sides by the mass, and you end up with g equals v squared over r. Starting to look a little familiar, but okay, multiply both sides by r, and we get gr equals v squared. And then we just take the square root, and we get that v equals the square root of gr. Whoa. That's the critical velocity. That's what it takes to loop the loop. Yeah, that's what it takes to loop the loop, where it's the normal force keeping you in a circle. That's the... but we said that in that situation at the top, it was just weight acting on it there as it kind of breathes the top on the top of the loop. We have a similar situation with an object in orbit. The only force acting on it is the force of gravity, and so therefore the speed, the horizontal velocity that you need to get to is the square root of gr, where g is 9.8 meters per second squared, and r is the radius that is the distance from you, not to the surface there, but from you to the center of the Earth. Okay? Really interesting that the mass just totally cancels out. It's just that you need to get to that velocity. Now, if you have a larger mass or a smaller mass, then in order for you to accelerate up to that velocity, it's going to require more rocket fuel or less rocket fuel or a different type of rocket altogether. So when we say the mass doesn't matter, I mean, the mass does matter because you're going to have to be accelerating up to this velocity, but it doesn't matter in terms of what velocity you need to reach. So that's kind of interesting there. One of the things that students might say is, they say, well, if you're up there in orbit, then you're weightless and there is no gravity. And that is just not true. Even if you are, hundreds of thousands of miles away from the Earth, the Earth is still pulling on you. There is still gravity. We'll talk about that in the next lesson. The moon is much farther away from the Earth than all of our satellites, and it's kept close to the Earth because of gravity. So gravity is still totally a thing. This thing still has the weight force due to gravity, and we'll talk about the actual formula for gravity here in a little bit. So I just want to make sure I talked about everything that we wanted to mention. Now, let's say that box had people in it. Maybe it's not just a satellite. Maybe it's a space station, and there's someone in it. Now it just kind of looks like a coffin. But anyway, that person and the box, the satellite, the spaceship, the rocket ship, the space station, as it's going around, is falling. And this satellite, or the space station, is falling. Technically, they're falling here, they're falling here, they're falling here, they're falling here. But they're just constantly falling, but never getting any closer to the Earth. So it's very much the same situation that you would feel in there as if you were on an elevator, that all of a sudden all the cables broke in a horrific accident, and it just started falling towards the bottom of the elevator shaft. You would be able to float around for a minute, maybe a few seconds, and push off, and you just be like, all right, this is great. So it's not accurate to say that if you're in the space station or if you're in the shuttle, well, we don't have the shuttle anymore, but if you're in a SpaceX Dragon capsule, that you are weightless. You still have weight. The Earth is still pulling on you. What you don't have is any normal forces pushing back up on you. So your apparent weight is zero. Your normal force is zero. We mentioned in a previous lecture that is your apparent weight. So you are of apparent weightlessness. But you do have weight. Gravity is still pulling on you. And the reason why they're able to fly around and do all that sort of stuff like that in 0G is because they're constantly falling and the normal force is not acting on them. Okay? There's some interesting ways you can introduce artificial gravity and things like that. Science fiction books do a really good and fun, interesting job simulating that. So there you go. I want to talk about orbit. I want to talk about weightlessness. This really cool velocity formula came up again. And looking forward to our next lecture. We'll be talking about Newton's law of gravity, which is going to give us some really neat numbers. See you then.